For example, again, x plus y plus s2 is equal to 80. Since again we have a less than equal to sign. Similarly for x plus s3 is equal to 40, as we have a less than equal to sign here. And then finally, let me just make a line here, separate it. Yeah. And then we have x comma y, which is greater than 0. So which we can write it as follows. S1 comma S2 comma S3 is greater than equal to 0. So this is our constraints in standard form. So we convert basically everything to standard form. That's our second step. Right. Now coming to the next step, right? So step 3 is to create the initial table. So create table. So the way this works is, first we have x, and we have y, and we have s1 and s2, s3, and then we have an RHS term, right? Then we have z, s1, s2, s3. Now what we do is, I'll just make the lines where it's clear. So this is what we have. Now we substitute these values from the older equation. Just put it over here. So now what we have is our x becomes -3, right? In our z, our x is basically what? It's going to be so let's say this is going to be 3, the coefficient. This is going to be 2. Then we have 0, 0, 0. And RHS is also 0. S1, we have 2, 1, 1, 0, 0, and 100. And we have S2. This we are taking it basically from here. The coefficients, the coefficient would for S2 would be the second equation, which is 1, 1, 0, 1, 0, and right hand side would be 80. Then we have 1, 1, sorry, 0, 0, 0, 1, and 40. I hope this is clear. We are basically taking the constraints from here in the last case. Now, next, we basically choose the pivot column. So our pivot column would basically be the most negative value in the 0, which is, this is -3 and -2. So since the most negative value in the 0 is -3, so we choose this as a pivot column, right? So this is a pivot column. And pivot row is basically the minimum ratio of RHS to pivot column. It's 40:1, right? So 40 divided by 1. So 0 divided by -3 is 0. Then we have 100 divided by 2 is 50, 80 divided by 1 is 80, 40 divided by 1 is 40. So hence this becomes our pivot row. Pivot on the element. What did the operations researcher say when his computer crashed? It's a constraint violation. And why did the operations researcher go to the doctor? He had a problem with his objective function. What do you call an operations researcher who is an expert in linear programming? A simplex master. So now, in order to make this 1, what we do is we divide everything by -3. So this would basically become 1 in the next step. So this becomes 1. This becomes 2 by 3, and so on. This becomes all zeros. So after doing the pivot operation by dividing everything by uh, the pivot row, finally what we get as the table is as follows. We have x, y, s1, s2, s3, and RHS. And then we have z, y, s2, and x. So let me just quickly draw down the next step in the simplex method, where basically taking in x, y, s1, s2, s3, and RHS, and on the rows we're taking z, y, s2, and x. So this is how it looks like. So this value becomes 0, 0, 0, 1, 0, 1, 0, 0, 2, 1, minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1, 0. We have so this is basically minus 1, this is minus 2, this is 1, this is 1, and this becomes 160, 20, 20, and 40. Hence, our optimal solution is when x is equal to 40, y is equal to 20, and we basically plug our x and y values into the equation. Z is equal to 3 into 40 plus 2 into 20, and this value becomes 160. Hence, we get our optimal z value. So this is what we wanted to optimize for using simplex method. Why did the operations researcher get lost? Because he couldn't find the optimal route. What did the operations researcher say when his model didn't work? It's a feasibility issue. Why did the operations researcher become a chef? Because he loved optimizing recipes. What do you call an operations researcher who is an expert in queuing theory? A master of waiting in line. Next, we have the transportation problem. So your task is basically to set up a small cost matrix, two sources, and two destinations. And show northwest corner method. Just take a look at this method and you can basically try practicing it. Next, we go on to the next topic, which is queuing basics. So you have queuing basics. So quick intro to this. What do you call an operations researcher who's an expert in queuing theory, a master of waiting in the line? Why did the operations researcher go to the gym? To optimize his fitness function. What did the operations researcher say when his team didn't work together? We need to improve our coordination constraints. Why did the operations researcher break up with his girlfriend? Because he realized he was stuck in a local optimum. What do you call an operations researcher who's always on time? A punctual optimizer. Why did the operations researcher go to the art museum? to appreciate the beauty of linear programming. What did the operation researcher say when his model was too complex? I need to simplify the constraints. Why did the operations researcher become a musician? Because he loved optimizing harmonies. And what do you call an operations researcher who is an expert in dynamic programming, a master of sequential decision making? Why did the operations researcher go to the doctor? He had a problem with his shadow price. What did the operations researcher say when his team was working well together? We have got a great synergy that's greater than the sum of its parts. So, suppose you are at a coffee shop with a single barista or a waiter. Customers arrive at a rate of 2 per minute. So, let's say our lambda is equal to 2, which is basically customer arrival rate. And the barista can serve 3 customers per minute. So, mu is equal to 3, which is basically serves per minute. So, what is the utilization of the barista? So, utilization is given as follows, is basically going to be equal to rho is equal to lambda by mu, which is equal to 2 by 3, which is equal to 0.67. So this means that the barista is busy 67% of the time. So 67% of the time, you will have that the barista is serving coffee to his customers, right? Now let's calculate the average wait time. So the average wait time would basically be rho upon mu into 1 minus rho, which is basically equal to 0.67 divided by 3 into 1 minus 0.67. And this value becomes close to 0.68 minutes. And what this means is that on average, customers have to wait approximately 0.68 minutes or about 41 seconds in line. So 41 seconds in line, the customers have to wait. So this is what we call as a basic queuing example. I hope this is clear. So now we take a break and basically recap and practice. So we have first solve a linear programming problem. Max of z is equal to x plus 3y with constraints of x plus 2y is less than equal to 6 and 3x plus y is less than equal to 9. Second, we try northwest corner method for transport with 3 cross 3 matrix. And third is to compute average wait time in m by m 1 with lambda is equal to 2 and mu is equal to 5. So yeah, that's pretty much about what we have here. Next topic will be circuits and network theory. Thank you.